Collat's conjecture is quite a fun process. You start with some number. If it's even, you divide by 2. If it's odd, you multiply it by 3 and add 1 to it, and you continue. So this is an interesting process, and the conjecture states that eventually you will end up in the ending state being 1. So why is the ending state 1? Because, well, once you reach 1, it's an odd number, times 3 plus 1, you are going to go to 4. 4 is even, so you'll come back to 2, and then back to 1, and so on and so forth. So you've essentially started cycling in this process. But the conjecture states that anywhere you start, you're eventually going to come to this cycle of 3 numbers. And this has been quite interesting for a long time, but as the cartoon indicates, you probably don't want to get too obsessed with that. In fact, there's more interesting processes that we can talk about. Well, what could be more fun than the Collat's conjecture? Well, what's the type of process that a drunk man would take while walking on a street? It turns out that might have quite interesting properties in and of itself. So that's what we're going to talk about today, believe it or not. So let's get to it, but let's motivate this by a well-known problem. Well, we're going to talk about the two-sat problem. And to talk about the two-sat problem, we'll first have to set up some definitions. So what is a Boolean variable? It's a variable that can take one of two values, either 0 or 1. And we're interested in a logical formula. And when the Boolean variable appears in the logical formula, it's called a literal. And of course, it can appear in two ways, either the positive form or the negative form. Okay. And in particular, in the two-sat or more generally in the k-sat problem, we're interested in logical formulas that conform to 3CNF, or rather the CNF format. What is that? Well, it's a conjunction, basically, and of several clauses, and each clause is a disjunction of literals. In the context of 2CNF, each clause will have exactly 2 literals. So here we see an example of a 2CNF logical formula. And the SAT question is, can we assign truth values to the variable so that the formula will evaluate to true? Another way of stating it is, can we assign truth values so the formula can be satisfied? So here we see a very, very simple algorithm. And I call it a "can you believe this works" algorithm, because the first time I saw it, it seemed a bit magical. So here's the algorithm. The input is of course, a 2CNF formula, and there are n variables in it. And how do you find out whether there's a satisfying truth assignment? Well, you start with some arbitrary truth assignment, and you keep repeating this process, okay? And you repeat up to 2mn squared times, where m is a suitably large integer, or until you find a clause that is satisfied. Of course, if you find a clause that is satisfied, you can terminate, and that's what we do here. But let's not jump ahead. So we repeat this process. In each time we repeat, we choose an arbitrary unsatisfied clause. Of course, if you had found a truth assignment that satisfies the formula, we'll be out of this loop. So there's always going to be an unsatisfied clause if we are inside the loop. And so we find one such clause, and we look at the 2 variables in that clause. Remember, this is 2CNF, so there are 2 variables. And we just pick one of them uniformly at random and flip its truth value. and then again check if the truth assignment is a satisfying assignment. And if it's not, we repeat this process, and we repeat this for this many times, 2mn squared times, until we either exhaust the number of trials, or we simply or we find a truth assignment. And of course, if we find the truth assignment, we'll return it. But if we don't find the truth assignment, we're going to conclude that there is no satisfying truth assignment. And this is where it seems a bit magical to me. So let's make some statements about this algorithm. First of all, it's quite clear that it's always correct when there is no satisfying truth assignment, because in that case, we will always be exiting this loop having not found a satisfying clause, and so we would be executing line 4 and saying that there is no truth assignment. So that's not very surprising. The surprising part comes when we have a satisfying assignment. If such a satisfying assignment exists, satisfying truth assignment will be reported with probability at least 1 minus 2 raised to the minus m. And here m is an arbitrary number, so you can notice that you can make this probability arbitrarily close to 1, and it of course approaches 1 exponentially fast in m. So this seems surprising. So let's actually try to figure out why this is the case. And for this, we need to build a little bit of theory, and this is where it would help for us to understand this random process. So let's start by defining a stochastic process. It's nothing but a collection of random variables, and these random variables are parameterized by this parameter t, and the most useful way to interpret this parameter t is time. So this variable therefore can be thought of as the way a random variable changes over time. And if this random variable x takes a finite or countably infinite number of values, then it's called a discrete space stochastic process. Now, these values that x can take are often called the states of the process. So you can think of this process as going from one state to another state to another state over time. Okay, and we are most often interested in processes where the state space is discrete, meaning it's finite or countably infinite. And of course, the parameter t also is often finite and or countably infinite. And such processes, we call them discrete time stochastic processes. And so we can interpret xt as the state at time t. Of course, our primary focus will be on discrete time and discrete space stochastic processes. And t takes integral values starting from typically t equal to 0 to t equal to 1 and so on. We are interested in a discrete time and discrete space stochastic process that has an interesting memorylessness property. And here's what that property is. Let's suppose we are interested in the event that the state of the process is at 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 time t. Well, how could it have reached that state? Well, obviously it depends on the past history. And of course, if it might depend on the entire past history. So that's this probability stated here. And this is its entire history. Now, if this stochastic process was memoryless, then this probability conditioned on the entire history would end up being the probability that the state would be at 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 time t, given only its previous state. And that's sufficient, that xt minus 1 equals AT minus 1. So the probability that the current state is AT only depends on where the process was in the previous time step. And the history beyond that is has no bearing at all. And therefore these transitions, probability transitions, since they don't have any, since the history doesn't have, beyond that one previous step does not have any bearing, this probability can simply be written as P AT minus 1 to AT, because if you are at AT minus 1 at time t minus 1, then with this probability you will be at state AT at time t. And such a stochastic process that has this memorylessness, that forgets this past history beyond just the one previous step, is called a Markov chain. And these are very, very elegant and useful because they model a lot of real-world processes, and they're also elegant and easy to analyze, and end up being quite useful for many algorithmic purposes. So this probability P AT minus 1 to AT is called the transition probability. Basically, it's a probability that if you are at state AT minus 1, then you will move to state AT with this probability. Let's now consider the Markov chain with a finite state space. In particular, let's say that it has n states and they are numbered from 1 to n. Then its probability, its transition probabilities can be captured by a transition matrix, in which is an n by n matrix. If you look at the entry I comma j, it's a probability, and it denotes the probability that you would reach state j in one step, given that your previous step was state I. So let us denote the probability distribution over the state space by this vector of probabilities, and here P0 of t is the probability that the Markov chain will be at state 0 at time step t, state 1 at time step t, and so on up to state n at time step t. Notice that when you multiply the vector, the distribution vector, with the transition matrix, we're going to get the distribution vector at time t plus 1. We can extend this further. So the m step transition probability from I to j is defined as follows. Now suppose you are at state I at some time t. This m step transition probability gives you the probability that at time t plus m you will be at state j. Okay, so it's the probability that the Markov chain will move from state I to state j in exactly m steps. Okay, and so this let's consider the matrix whose entries are these m step transition probabilities, and that we're going to denote by p superscript m within parentheses. Now, using this, the fact that if you take the current probability distribution and multiply it with the transition matrix you will get the probability distribution at time t plus 1. Using this formula, a good exercise would be to show that this this matrix, whose entries are the m-step transition probabilities, can be obtained simply by taking the transition matrix and raising it to the power n. Quite naturally, as a consequence, if you take the probability distribution sometime t and multiply it with the transition matrix raised to the power m, you will get the distribution, probability distribution at time t plus m. So let us quickly recap. We've defined what we call a stochastic process. It's basically, of course, we are interested in discrete time, discrete space stochastic processes. So you can interpret this as a random variable that takes various states through time. And we're particularly interested in Markov chains, which are stochastic processes that exhibit the memorylessness property. So there's a clear probability with which you transition from one state to another. And you can also make these large m-step transitions. Well, essentially, they are just the probability transition matrix raised to the power m. So you can view this m-step transition probabilities themselves as a sort of a Markov process. So notice that the key thing here is, in general, going from one state to another. And these state transition probabilities provide you the probabilities with which you go from one state to another. And so quite naturally, we can view this whole Markov chain, we can view a Markov chain as we can view this Markov chain as a graph. Okay, so a quick exercise for you would be to think of Markov chains and think about how we can use graphs to represent Markov chains. So, for example, what will be the vertices? Of course, this is not rocket science. It's your vertices are going to be the set of states that the Markov chain can take. And is this graph that represents the Markov chain going to be directed or undirected? Well, typically it's going to be directed, because the probability of going from one state to another need not be the probability with which you come back from the other state back to the original state. And therefore, you may want to distinguish the directions. So you probably want a directed graph. And will it be weighted? Yes, because you would probably want to capture the probability, the transition probabilities using weights. And what can you say about the weights of edges going out of a vertex? Well, notice that these are probabilities, so they will have to sum to 1. On a similar vein, what can we say about the probabilities, or rather the weights of edges that are entering into a vertex? Will they also add up to 1? Think about it. Here they don't have to add up to 1, because you could be entering into a vertex from a variety of different other states or vertices, and there is no reason for the weights on the edges, incoming edges, to add up to 1. And of course, can the graph have self loops? Yes, because there is nothing that says that the Markov chain should necessarily move to another state at each time step. There you could have a non-zero probability with which the Markov chain remains in its current state, and these can be modeled using self-loops. Essentially, this Markov chain can be viewed as a drunkard taking taking a random walk on this graph. Okay, and if he is at a node in the graph, then he will move to a neighboring node in accordance to the probabilities, the weights on the outgoing edges. So here's a simple warm-up. Let's consider a Markov chain in which the states can be arranged. So the states range from 0 to n. And they are arranged in linear fashion, starting from 0 here to n over here. And if you notice, at any intermediate state, with probability half, you move forward. So for example, if you're at state j, you will go to state j plus 1 with probability half, and with state and with probability half, you will move to state j minus 1. Okay. So an interesting question that we can ask is, how long does the drunkard take to go from one end of this Markov chain to the other? So let's say he starts at state 0. How long does he take to reach state n? Okay, and this question turns out to be quite interesting and also quite useful. Let's use the random variable zj to denote the number of steps that the drunkard will have to take, these random steps, to reach state n, having started at state j. Of course, if he, since he's going to be doing random walk, he could also be moving. Sometimes he'd be moving backwards, sometimes he'd be moving forwards. So we want to know how long it will take before he reaches n. Okay, and we use hj to denote the expected value of zj. And we are particularly interested in h0, which is the expected number of steps that this drunkard will take to reach n, having started at the very end, very extreme other end, at state 0. Okay, so if you consider any intermediate state j, let's look at hj. From state j, there are two possibilities. With probability half, we can go to state j plus 1. So with probability half, we'll make one step, go to state j plus 1, and then you can simply count the number of steps to go to state n from j plus 1. So this is the probability half, and with that probability half, we'll make that one step to j plus 1, that's this one over here, and then having reached j plus 1, we're going to take zj plus 1 number of steps to reach state n. So this is, we've counted for half of the probability. Now with the other half of the probability, we're going to move to state j minus 1. Okay, so that's this other half. And we're spending that one step moving to j minus 1. And having moved to j minus 1, we'll spend zj minus 1 number of steps to make our way to state n. So hj can be written as the expectation of these two random variables weighted in this manner. So with probability half, you spend one step going to j plus 1 plus the time it takes to go from j plus 1 to n, and with probability half, you take one step to state j minus 1 and then the amount of time it takes to reach state n. And the expectation of these two possibilities is going to be hj. And of course, this can be expanded out to hj minus 1 divided by 2 plus hj plus 1 divided by 2 plus 1. So that's a quick exercise for you to figure that out. And of course, if you're in state 0, you really cannot go to state -1 because there is no such state in this particular Markov chain. So the only option you have is to spend the one time step going to state 1, and from there h1 captures the time it takes to, the expected time it takes to reach state n. So that's one of the base cases. And the other base case is hn. If you've already reached state n, then you're already there. So in 0 time steps, you will reach state n. So hn is equal to 0. So now what we have is a system of linear equations. So we have hj's for intermediate values of j, and h0 and hn. And a simple exercise for you using induction would be to prove that hj for j ranging from 0 to up to n minus 1 equals hj plus 1 plus 2j plus 1. So this is basically the solution to this system of equations using simple induction. And applying the base case, we can actually work out the probability, or rather we can work out the expected number of steps that the drunkard will take to reach state n, having started at state 0. That's our h0. Well, we know that h0 equals to h1 plus 1. But applying this formula inductively, h1 evaluates to h2 plus 2 plus 1, and so on. If we work our way, we end up with h0 equaling n squared. So what this says is, if you start at state 0 and make these random walk transitions, you will reach state n in expected n squared steps. Okay, so this is quite interesting, but why is it useful? Well, let's go back to an algorithm that we looked at for 2SAT. Okay, so we have the input 2CNF formula on n variables. We started off with an arbitrary truth assignment, and we iterated up to 2mn squared times, or until we found a satisfying truth assignment. And every time we didn't find a satisfying truth assignment, we picked an arbitrary clause and randomly picked one of the variables and flipped it. And we kept doing this process until we either found a truth assignment within 2mn squared time steps, or we just declared that there is no satisfying truth assignment. Okay, and we claimed that this algorithm, if it has a satisfying, if the input formula has a satisfying assignment, will find that satisfying truth assignment with with overwhelmingly large probability. So basically probability of the form 1 minus 2 raised to the minus m. Okay. And why is it true? We're just going to quickly sketch the proof, and we'll see how Markov chains are useful in this process. So assume, so notice that if the formula is not satisfiable, then the algorithm is always going to be correct. It's always going to say, well, there is no truth assignment. So we're only interested in the case where there is a satisfying truth assignment. And so let's just pick one such satisfying truth assignment, and let's call that T. And let's look at the execution of this algorithm at some point in time. If you consider any unsatisfied clause, at least one of its variables does not match T. And this is quite obvious. Why is that? Well, let's look at an unsatisfying clause of the form, let's say xj or xi. Okay. And if the let's say both xj and xi match the truth assignments they have in T, well, then this clause will be a satisfying clause. So both of them cannot be matching their assignments in T. So at least one of them will have to be different from their truth value in T. Okay. Well, so what? This is not very surprising, but why is this important and why is this useful? Well, it's very useful because now we can say that if we choose such an unsatisfying clause, which is what the algorithm does, it chooses one of these unsatisfying clauses and picks one of these variables uniformly at random and flips their value. So if, let's say, xi is the variable whose current truth assignment does not match T, then with probability half, we're going to be flipping xi's value, and so with that probability half, we're going to move the current truth assignment one step closer to T. Of course, it's also possible that both xi and xj are different from their assignments. Current assignments are different from the assignment in T, in which case this probability actually becomes 1. Regardless of which variable we choose, we're going to get closer to T, one step closer to T. And so that's why this probability that the truth assignment is closer to T after line 2b, that's this line 2b in the algorithm where we pick a variable uniformly at random and flip it. So the probability that the truth assignment gets closer to T after line 2b is greater than or equal to half. Okay. Now let's try to take this insight and frame this into a notion that we know, basically a random walk. Okay. Along the way, what we're going to do is we're going to make some simplifying assumptions, but we're always going to make pessimistic assumptions, so that whatever claim we have at the end is going to only be worse than the actual true claim. Okay. So let xi denote the number of variables in the truth assignment after the ith iteration that match T. Basically, why do we need this xi? Because we want to be able to capture how close we are to matching T completely. Okay. So at time step I, xi denotes the number of variables in which our current truth assignment matches the assignment T. Okay. We've already seen that the algorithm will move one step closer to T with probability greater than or equal to half. So we're going to modify this just a little bit So we are going to be a bit pessimistic about setting up the random walk. Let's assume that xi minus 1 equal to j. In other words, at time step I minus 1, we have j matches with the truth assignment t. Okay, so now what is the probability that xi equals j plus 1? We're going to assume that that's a half. And what's the probability that xi equals j minus 1? That's also equal to a half. So from state, you can think of this as a random walk in which from j with probability half we go to j plus 1, with probability half we go to j minus 1. And this extends for all j, so with probability half we'll go from j minus 1 to j, with probability half will go from j to j, j plus 1 to j as well, and so on. So this exactly matches the random walk on a line that we've already seen before. So what we know is this that this pessimistic Markov chain actually terminates in n squared steps on expectation. So this is what we are going to use crucially to prove that the algorithm in fact finds the satisfying truth assignment with such overwhelmingly high probability. Okay, so that's a simple exercise for you. So you basically have to use the Markov inequality to prove that the probability with which the algorithm does not find the truth assignment after 2 n squared steps is at most a half. And then when we repeat it n times, we can reduce this probability down to 2 raised to the minus n, which gives us the result that we want. So before we conclude, I would like to point out one thing. Why is it that we are not using this probability? Instead, we're choosing a more pessimistic option. Well, as it turns out, if we view this stochastic process using the actual probabilities, it's not a Markov chain. The probability with which we transition to a particular state with a certain number of matches with the truth assignment t may depend on many historical facts. So we simply don't have the tools to analyze it as elegantly as we can if we view this process as a Markov Markov chain. So that's the reason why we are being a bit pessimistic, but in return we're getting the argument to a form that we can analyze more elegantly. So that brings us to the end of our discussion on Markov chains, at least the first segment, and we will be talking a little bit more about Markov chains in subsequent segments, and hopefully we will also get to the point where we discuss a big data application that uses